Hi everyone, it's my great honor to introduce today's speaker, Troy and Mike. Troy is Robert Haslam and Bradley Dewey Professor of Chemistry at MIT. His research focuses on the development of a new methodology, many DFT-based methodologies that provide an accurate description of excited electron motion in molecular systems. This includes the widely used constrained DFT method Troy and Mike will talk about today. Troy has been recognized by many awards, including the Sloan Research Fellow, the Packett Fellow, NSF Career Award, and the Wiley IJQC Young Investigator Award. Mike is a PhD student with Troy, and his research has been focused on the extended spin boson models for approximate quantum dynamics of condensed phase electron transfer, and the computational screening of transition metal oxide materials for heterogeneous catalytic water splitting, and the utilization of nitrogen heterocycle polymers as anchors to surfaces. Now let's hear from Troy and Mike.
Well, thanks, Yihan. I think the way that we'll structure this, this is Troy, and I'll do a brief introduction just to the methodology of constrained DFT, why you might want to use it, what it's good for, illustrations of the kind of accuracy that you can expect from it and the kind of accuracy you can't expect from it. And then Mike will go on and do a sort of short tutorial that will be just sort of going over the details of how you specifically use it in Q-Chem. So first things first, what would constrained DFT be good for? And a lot of constrained DFT's usage is driven by the idea of a diabatic state. How do I go to the next slide here? Okay, there we go. So diabatic states are, generically speaking, states that have the same physical character at different nuclear geometries. So the first place that a lot of people are introduced to the idea of diabatic states is with ionic bonds. So you think about sodium and chlorine atoms, and if they were to come together as neutral atoms, they would form a fairly weak bond, so they would have fairly shallow potential energy well. And we all know that this isn't quite the right picture for sodium and chlorine because they can exchange electrons. Sodium likes to give up an electron, chlorine likes to have an electron. And so if you think of them as ions, they have a much stronger ionic bond where sodium is positive and chlorine is negative, and this bond is held together by the attraction between positive and negative ions. And that's more stable when the atoms are close to each other, but less stable when they're far apart. So the energy of that state should look something like this red curve. It should cross this neutral curve somewhere at some intermediate distance. And these two states are, by construction, diabatic states. They don't change character as I change the bond length. So the one state stays neutral, the other state stays ionic, no matter which one is stable at a given distance. And so these are useful chemical concepts, although in many times in electronic structure, what we're actually interested in are adiabatic states. So the adiabatic state is going to be the one that's the lowest energy state at every value of R. And so we could obtain the adiabatic states here. We say, well, there are two different physical states. So in quantum mechanics, that means my Hamiltonian could be represented by a 2x2 matrix, where the basis states are respectively the neutral and ionic states. So I would have a matrix that looks like this. It's got the energy of the neutral state, the energy of the ionic state, and some coupling between them. And if I found the lowest eigenvalue of that matrix, it would give me an adiabatic state that looks like this lower green curve here. So it would look like a neutral state far away and an ionic state close in. And there would be another eigenvalue of this matrix that would look like the upper green curve here that would just do the opposite. So that's one reason that constrained DFT is going to be useful for you. Another one is because these same kind of localized states are useful when you start talking about bonding. So this is, for example, the case when you talk about valence bond theory. But if I talk about the simplest bond I can think of, which is the bond in H2+, I can think of two localized charge states that make this bond work. One where the charge is localized on the left, one where it's localized on the right. And just like was the case for ionic bonding, in this case, my Hamiltonian is a little 2x2 matrix that involves the energy of the left state, the energy of the right state, and the coupling between them. And now here, as you can see, the state where the charge is localized on the left is going to overlap with the state where it's on the right. So I need to have not just an eigenvalue problem here. I don't just need the eigenvalues of this matrix, but I need the generalized eigenvalues with some overlap matrix. It's also going to be a little 2 by 2. So I find the generalized eigenvalues and eigenvectors here, and those are going to give me the adiabatic states, which in this case are going to be proportional to left plus right and left minus right, which are respectively the bonding and anti-bonding orbitals here. And again, the observation here is that the coupling is important. In this case, the coupling between the left and the right states determines the splitting between these two adiabatic states. So if you have a strong coupling, it's going to mean you have a very strong bond and a strong anti-bond. If there's a weak coupling, the bond will be weak. And so you'd like a tool that lets you get at states like this left state or the right state, or like the ionic state and the covalent state for sodium chloride. And that's what constrained DFT does for you. Generically speaking, what you recognize is that if you'd like a state where charge is localized, so a state like donor plus, acceptor neutral, you can obtain that by constraining there to be a positive charge on the donor. So in all calculations, of course, the total number of charges is fixed. So if there's overall a positive charge and you constrain that positive charge to be on one side, obviously the remainder of the molecule has to be neutral. And so this is the generic idea for constrained DFT, which now I'm going to try to illustrate two different ways. So first, I will illustrate this with a picture using a mascot molecule, this one right here, and then I'll try to do it with some equations. So for this mascot molecule, this is a tetrathiafulvalene derivative. I could imagine taking an electron off of this, so making this a cation, a radical cation, and then for whatever reason, I might want to localize that positive charge on the left-hand side. So I'd call the left-hand side my donor, the right-hand side my acceptor. And what I'd like to be able to tell the computer is localize the charge on the left. And so in order to do that, the way that you do this in constrained DFT is, first of all, you have to tell the computer which atoms are on the donor. So you have to tell it that the atoms on the left are on the donor. And by telling the computer that those atoms are on the donor, you're implicitly saying that at the end of the calculation, the partial charges on these atoms better add up to plus 1.000. That's what I mean by donor being positively charged. And so then what the computer is going to do is it's going to go off and look for the lowest energy state that satisfies the constraint that you've put in, and then it will return a charge density that looks roughly like the picture here, where the positive charge is localized on the left, just as you asked. And what we've done is we've implemented this into Q-Chem and also into NW-Chem, but this is the talk about how it's used in Q-Chem. So we've implemented charge constraints, just as I talked about here, where you can localize a charge on part of a molecule, or if you have two molecules, you can make sure the charge just stays on just one of the two molecules. Or you can localize a spin, so you could make one fragment spin up and the other one spin down. And you can do this on one fragment in a calculation, or two fragments, or three fragments. You can constrain the charge, or the spin, or the charge and spin, various combinations of things. So the result then is that if you're given a molecule like this, you can specify a local charge and a local spin on the molecule in a meaningful way. Now, mathematically, it's probably interesting to think about how we do this. So the way that this is done mathematically is that in density functional theory, you start off with an energy that, as the name implies, is a functional of the density. And we want to now just add a constraint that says that there's some property, which is specified by some operator O, and we want that property to take on some value n that we've specified. So in this case, this would be an operator that measures the charge, and we want, when we average that over the electron density, we want to get +1. And so we add that constraint times the Lagrange multiplier, and now we look for the stationary point of this super Lagrangian. And so if you run through the math on that super Lagrangian, you want to make this stationary with respect to the density and also the potential. And the density equation is the interesting one. So if you make this stationary with respect to the density, this results in a modified equation for the Cone-Sham orbitals. So with no constraint, you would have h phi is equal to epsilon phi for each of your Cone-Sham orbitals. And now we've got this additional term here that comes from our operator and our Lagrange multiplier. And it's important to note that this operator is just a potential. It just depends on position. It doesn't have any gradients in it or anything like that. And so this potential is the thing that actually enforces the constraint, and that's a very nice theoretical feature because density functional theory works well with external potentials. It gives you the right ground state density and the right ground state energy. And so this was an idea that was introduced back in the mid-'80s. We were sort of the first people to actually do a realistic implementation of this in the early 2000s. So a couple of illustrations of where this could be useful in a moment, but I also want to just come back and touch here on this constraint potential so that you can get a physical intuition for what's going on here. So if you took a look at a molecule, say like this one, which is a donor on the left and an acceptor on the right, and you tried to make a state that looked like donor plus, acceptor minus, well, what constrained DFT is going to do is it's going to develop a potential that will create a state that looks like donor plus, acceptor minus. And so it's instructive to look at what that potential looks like. So we're constraining the charge over here, constraining the number of electrons on the acceptor to be -1. And the resulting potential looks like this. So it's basically 0 on the part of the molecule that's not constrained, and then it very, very rapidly changes to some other value on the part of the molecule that is constrained. And the depth of this potential is controlled by that Lagrange multiplier. So you can sort of think about it, there's sort of a step function here. Electrons are going to want to go downhill on this step function, which is going to tend to force electrons from the donor towards the acceptor. And at convergence, once you've optimized, once the computer figures out just the right depth of this potential, you'll end up with a situation where there's exactly 1 negative charge on the acceptor and a positive charge left behind on the donor. And you may ask, well, what determines the shape of this potential? Well, the shape of the potential is determined by how you've defined atomic charges, because that's how the computer knows that the donor is positively charged, is it looks at the atomic charges. And so the shape of this potential is actually determined by whether you use, say, Mulliken charges or Levdine charges or Becky or any of a host of different charges. They all look qualitatively similar, but quantitatively the potentials are going to look slightly different. Okay, so a couple of illustrations where this might be useful. So the first thing you can look at are charge transfer excitations. So as many of you may know, if you use time-dependent density functional theory for a charge transfer excitation, it tends to under-predict the energy, at least if you use semi-local density functionals. So an example here is charge transfer in this molecule from the left-hand side of the molecule to the right to create a negative, or sorry, from the right-hand side to the left to create a positive charge on the right and a negative charge on the left. If we do this with time-dependent B3 lip, we predict an energy of about 1.3 eV, whereas the accurate energy is more like 3.8. And of course, we could do this using constrained DFT. We constrain the left-hand side to be neutral, and that gives us the ground state. We constrain it to be negative. That gives us the excited state. We take an energy difference, and we find that if you do that, you get 3.8 eV out of constrained DFT. So constrained DFT, even with the same functional, I think I might have said this is time-dependent B3 lip. It's just time-dependent B lip gives 1.3 eV. If you use constrained DFT with the same B lip functional, you get a much better answer. A slightly different example, again looking at a charge transfer excitation, are a couple of molecules here, which one of these was one that I showed you before, this anthraquinone group here and this formanilide group. There were a couple of experiments that we looked at where there's a charge transfer excitation that goes from left to right on each of these molecules. And this occurs in solution, so that makes it a little bit more complicated. But constrained DFT works just fine with the continuum solvent models in Q-Chem. And so you can compute the energy, the free energy difference between the charge transferred state and the neutral state. All you have to do is make the charge transferred state and then relax the solvent to the charge transfer configuration and then make the neutral state and again relax the geometry in the solvent. And if you do this with B3 lip and a standard basis set and a continuum model of the solvent, you get a pretty good agreement between theory and experiment. So the experimental excitation energies are in parentheses, and the theories in front, and that's pretty good. And again, just to, I was going to say to drive home the point, if I did this with time-dependent DFT with the same B3 lip functional, we'd be out again by something like an entire EV away from the experiment. So that's one thing that you can use constrained DFT for, is predicting excitation energies. I now want to take one example of a situation where, well, does that mean that you can do any type of charge transfer with constrained DFT? And the answer is, well, no, not really. So here's another example of something you might want to do in terms of charge transfer. So this is an ion called the Kreutz-Taube ion. and there's a net one positive charge that wants to distribute itself either on the left or the right-hand side of this molecule. And there's a reorganization energy, which is basically the trapping energy for the electron on one side, or the positive charge on one side or the other. And we can do this in various ways. So I could define the constrained DFT states in one of three different ways. I could either localize the charge just on the metal ion here, which is this red circle. I could localize it on the metal ion plus its first solvation cell, which is this purple line. Or I could do an egalitarian, splitting the molecule in half and saying the left-hand side is where I want the positive charge, or the right-hand side. So that respectively gives me three different fragment choices that I could potentially use to define my charge localized states. And beyond that, I also have a few different choices for how I define atomic populations. So I could use Becky charges or Lovedean charges. So that gives me color-coded here. Blue gives me two different results. Purple gives me two different results. Red gives me two different results. And you see that the numbers aren't exactly the same. The trapping energies aren't exactly the same. But within about 1K plus or minus 1K cal per mole, the answer is about 3.5. So if you're willing to accept 1K cal per mole of fuzz, this worked. If you're not willing to accept 1K cal per mole of fuzz, you probably shouldn't be doing DFT. And so this is a case where the constraints seem to work. Now I'm going to give you a case where they don't work. So let's suppose I wanted to look at charge transfer within one water molecule. So I could think of a water molecule as being OH minus bound to a proton, H plus. So I could think of that configuration versus a configuration where this is OH neutral bound to H neutral. And I can figure out an energy difference between those two configurations. And here I have two different ways I could do that. I could use Becky charges, or I could use Lovedean charges. And those two things also give the same answer as long as you're willing to accept an error of about 116 kcals per mole. And generally, for chemical purposes, we're not willing to accept errors of 116 kcals per mole. So this didn't work. This did work. And the conclusion from this and other similar studies is that you can do this kind of thing. You can constrain the charges and assume that the charge on the Kreutz-Taube ion is an integer because the fragments are relatively well separated. They're separated by a few atoms. Whereas within a single water molecule, there's just too much overlap between the fragments. And so saying, oh, well, this is OH minus or OH neutral is pretty ambiguous. So that's one bit of advice about how you apply constrained DFT. Okay, so that's the easiest thing to get out of constrained DFT, which are energies. But sometimes we actually want to go beyond that because in these diabatic pictures, I need not just the energies of my states, but instead if I have two different states, say a reactant state and a product state, I might also want to know how strongly coupled those two states are to each other. So I need the electronic coupling between the two. And thus far, we haven't talked about that at all. So let's try to figure out how to compute this. Well, the coupling from quantum mechanics is now just going to be the matrix element of the reactants on one side and the products on the other with the Hamiltonian in the middle. But at this point, I'm kind of stuck when it comes to DFT because DFT gives me densities but not wave functions. So I can't directly evaluate this. So I need to figure out some approximation. So what we do to come up with an approximation is we say, well, the reactant state is not an eigenfunction of the Hamiltonian. It's not an adiabatic state, but it is an eigenfunction of a different Hamiltonian, which is the original Hamiltonian, plus some constraining potential, which I've denoted V sub r here, the constraining potential for the reactant. And so I can rewrite this by adding and subtracting the reactant potential, and then I can use the eigenvalue equation for the reactant to get rid of the Hamiltonian, and then I can rearrange things so that this matrix element just involves an overlap and then a one electron matrix element of the potential. So that's clearly a lot simpler. I have some hope that DFT might get this correct. I was a little asymmetric in how I did this. I did this always acting to the left, choosing the reactant state. If I symmetrize this, so I also include the result from the right, I get a slightly more complicated expression, but still quite simple. And so this is how we're going to compute couplings with the knowledge that, well, we've still got some wave functions here. What we're going to do is we're just going to use the Kohn-Sham wave functions at this point. So we'll stick in the Kohn-Sham wave functions for reactant and product and extract this coupling. And we, of course, have to test to see if this is any good. So we can test it for a small system, and we can say, all right, what if we talk about hole transfer between two zinc atoms? Well, as you change the distance between those zinc atoms, you expect the coupling to decay exponentially because the tail of the wave function decays exponentially. And sure enough, the coupling that we get out of that constrained DFT function decays exponentially. And if you compare this with an accurate result from configuration interaction, you see that the magnitude and the exponential decay match pretty well between constrained DFT and an accurate calculation. But of course, the DFT calculations are faster than CI calculations, and so we can take something much bigger, like this case, where you take, say, two ferrocene moieties and you separate them by an alkane bridge, and you just increase the length of that alkane bridge to push them further and further apart. And sure enough, you see that the coupling still decays roughly exponentially. It decays more slowly because there's this through bond interaction as opposed to just a through space interaction. But still, you can readily compute things that are fairly large to get this kind of a coupling. So that's so you can get energies, you can get couplings, but then getting back to this now, you can actually take that information, the energies and the couplings, and try to reassemble some very interesting information. Because now for example, getting back to the idea of H2+, you could say, all right, well, what if I try doing H2+, I get one diabatic state where I localize the charge on the left, one where I localized on the right. I can get the energies of those states and the couplings between the two, and I can get the overlaps between the Cone-Sham determinants. Can I do that? Can I get epsilon, V, and S from constrained DFT and then get this energy out by diagonalizing this little matrix? And the answer is you can, and the results actually look quite good. So for example, if we do that and we try to pull apart H2+ as a function of the distance between the hydrogen atoms, this is one of the scandalous failures of semi-local DFT, that B-lip and B3-lip show good results near equilibrium, but then dissociate into fictitiously low energy, partially charged fragments. And if we take those same two functionals and we do this constrained DFT plus CI approach, which we call CDFT-CI, you get the green and the blue, which agree very, very well with the exact results. So you can actually do some little CI calculations like this. And so you can extend this kind of an idea and treat just a more interesting kind of reaction. So even a generic reaction like the famous AX plus B goes to A plus XB reaction. So you can extend these ideas if you just simply say, well, what if we take the reactant state, which is AX weakly interacting with B, and the product state, which is A weakly interacting with XB. We take those as our reactant and product states in CDFT. We build our little CI matrix, which involves those reactant and product states sandwiching around the Hamiltonian. And we solve that CI problem to get energies of states and also wave functions for them. Well, this does a good job of something that people have long tried to do in DFT, which is because we're taking linear combinations of determinants, we can get some contribution of what's usually called static correlation. But because we're using density functional theory to build up the Hamiltonian, we get some contribution of dynamic correlation as well. And if we do it carefully, we can actually get a fairly good balance between the two. And so one thing you might want to look at here as a test of this is this activation energy, because you see that once I get my adiabatic energy, if I've done a good job of describing the reactant and product states and their coupling, I'll get a good estimate of this barrier height, which is actually a fairly difficult thing to predict in DFT. And so in order to do this, I need to back up and say in full disclosure that this system is going to actually violate the condition that I set out at the beginning. I told you that you wanted your fragments to be well separated, but here at this transition state, that's not going to be true. You're going to be at a place where AX and B are close to each other, they're overlapping, and so you have to make this work, you have to come up with a solution that deals with overlapping fragments. And this makes use of a concept that's known as the pro-molecule state. And I think it's best to illustrate this with an actual reaction. So here's a simple reaction. It's the SN2 reaction between fluoride ion and methylene chloride to make methylene fluoride and Cl-Cl-. And so the way that we do this to deal with these overlapping fragments, because here at the transition state, clearly this doesn't really look like reactants or products, so it's not clear how we just decide whether is this thing negatively charged, is this thing negatively charged. So the first thing to do is to fragment the system. So we fragment it into a reactants state, which of course is an F minus and a CH3Cl, and we fragment it into products, which is the FCH3 and Cl minus. And you'll note that the internal geometry of FCH3 is the same as its geometry at the transition state, and the internal geometry of CH3Cl is the same as its geometry at the transition state. And then we do calculations on these isolated fragments. So you get F minus, you get its density, you get the density of CH3Cl, FCH3Cl minus, and then you just add those densities back together at the transition state geometry, giving you what is called the promolecule, or the superposition of fragment densities. And then you take that density as your trial, and you take whatever potential you were going to use to evaluate the atomic populations. Again, that's going to look roughly like a step function. And you say, okay, using that definition, what's the charge on F minus here? It's not going to be -1 because some of the F minus charge leaks on to the other fragment. But you figure out whatever the charge on F minus is and whatever the net spin on F minus is, and then you use those constraints in your constrained DFT calculation to make the reactant density. And likewise, you do the same thing over here, making sure the charge and spin on Cl minus agree with your promolecule density, and then you use that to constrain your product density. And so if we do that, that kind of thing, we can actually take a library of barrier heights. So this is using the reference data from Don Trular's group for hydrogen atom transfer, heavy atom transfer, and nucleophilic substitution. So a total of 64 reactions. And what I'm showing you here are the mean error and mean absolute error for a variety of functionals for all these reactions. And in regular text is what you get with the functional, and in bold text is what you get with the functional plus CDFT-CI. And what you see if you look at any of the numbers is that they always get better when you do CDFT-CI. The barrier heights always, the agreement with experimental or ab initio barrier heights improves. And just to draw your attention to a couple of numbers, for example, if I do PBE with CDFT-CI, I get a mean absolute error of 4 kilocalories per mole. If I do just B3-lip, I get 5 kcals per mole. So this makes PBE better than B3-lip. And so it improves PBE by a factor of 2.5, which is significant. But if you start with B3-lip, you get even better. So you go from 5.1 down to 2.5. So you can definitely get accurate pictures of reaction barrier heights here. But you can go a step further and you can get excited states. So up to now I've been focusing out of CDFT-CI on this lower adiabatic state. But of course we get an upper adiabatic state here. And you can ask if there's anything interesting out of that upper adiabatic state. Of course there is. It's the excited electronic state. And here the splitting between these states is very, very sensitive to the coupling that we're computing. So if we're getting the coupling right, we should get these excited states correct as well. And so you go around and you search for things that might convince you whether or not these excited states are good. And one thing that we looked at early on were conical intersections. So these are a very common feature in excited states. They're very difficult to describe in DFT. And so here's a conical intersection that's not very chemically relevant, but is an interesting test case. So if you take H2O and you really torque it away from equilibrium, so you stretch the OH bond and change the HOH bond angle, you can make it have a conical intersection, as evidenced by this CAS-SCF curve down here. Here's the ground state potential energy surface. Here's the first excited state, and you see them coming together and touching and forming this little conical shape. So if you do this with TD-DFT with any functional, these particular results are, I believe, with B3-lip, the result is qualitatively wrong. You get a seam of crossings between the ground state and the excited state. It doesn't look right at all. But if you do this with CDFT-CI for the same functional, and you have to choose a few different states, so you choose OH minus, H plus, OH minus, OH neutral, H neutral, and then H neutral, OH neutral, total of 6 states, you get qualitatively the correct result. So there is a conical intersection at about the right energy at about the right place. And I want to point out two things. One is that earlier on in the talk, I had told you that CDFT by itself isn't good enough to treat something like OH minus H plus. But now, with these pro-molecule definitions, you see that we actually have something of a consistent definition that allows us to even treat strongly interacting fragments like that. So that's one important point. The other one is that CDFT-CI, you might say, well, if CAS-SCF gets this right, why should I do CDFT-CI? The reason for that is that CAS-SCF near equilibrium is terrible. So it's off by 0.4 of an electron volt near equilibrium, whereas CDFT-CI reverts to looking a lot like B3 lip near equilibrium. So its equilibrium energy is within 0.1 of an electron volt. So that's one of the really nice things about CDFT-CI is it gives you a sort of multi-reference way of getting ground states and excited states in DFT. And then the other big thing that we put a lot of time into is, okay, well, fine, you can get these energies, but in order to do things like molecular dynamics and to locate conical intersections, you really need to be able to get analytic gradients. And so we've implemented the analytic gradients. This is just a diagram of all the work that it took to do that. But as an informational piece, you can currently do gradients of CDFT-CI, and they are about twice as expensive as computing the Hessian for a normal density functional calculation at the moment. On top of that, I should mention that there also are gradients of just CDFT. Those are comparatively simple to implement and also comparatively quick to evaluate. So constrained DFT gradients are just about as fast as regular DFT gradients. So I think that finishes up my portion of sort of summarizing the capabilities. And so now I'll turn it back over to Yihan, who I think will probably hand it over to Mike. Or do it? Can I change the parent center? Yeah. Okay, let's see if I change it.
Yeah, you can do that, Troy.
All right, let's see. There, let's see. That work? All right, I think we're good. Go over to you.
Yeah, go ahead.
Okay. So Troy just told you all about the theory behind CDFT and CDFT-CI, and I'm going to go over a few illustrative examples about how to use this in Q-Chem. So the first example that I want to show is how to use just regular vanilla constrained DFT, and the example I picked is to constrain spins in transition metal dimers. So the system we're going to look at is a transition metal dimer containing cobalt-3 and chromium-4. So this molecular structure looks something like this, and this is something I had used for a project with this reference at the bottom here. And if you look at the crystal field splitting for this structure, you can draw some, you have octahedral geometry, so you should have an octahedral crystal field splitting, which means that you should expect the electronic structure in the D shells of these two transition metals to look something like this. Where all of the electrons on the cobalt metal are paired, and all of the electrons on the chromium side are not paired. There's some unpaired electrons. And normal DFT won't get this right. You'll see some kind of splitting between these two, or sharing of electrons between these two metals. So you can use constrained DFT if you want to get the energy of the actual states as crystal field theory would predict them. So the way we would do this is if you imagine dividing your molecule in half, where you have two different constraint regions, a constraint region on the left and a constraint region on the right. And so in the constraint region on the left, all of the electrons are paired. This entire molecule is neutral, so the total charge will be 0, and the charges on both of the constraints on the left and the right will be 0. The total spin of this entire molecule will be a total spin of 1, which 2 excess spins. I'm going to use a language of excess spins, meaning how many extra beta electrons or alpha electrons you have on each fragment, just because this is the language with which how it's implemented in Q-Chem. So this would be the total molecule as a spin multiplicity of 3 then, so 2 excess spins. But those 2 excess spins only live on the right-hand fragment. So what we want to do is we want to impose a constraint. So there are 0 excess spins on the left fragment and 2 excess spins on the right fragment. Okay. So to do this, we're going to go over to what the Q-Chem input for this thing would look like. So let's see, if we look at the input file, okay? So we have a molecule section. So these are the molecular coordinates for this molecule that I just showed you. So notice again, the total charge on this thing is neutral. Total multiplicity is a triplet. Total spin multiplicity of 3, which means we have 2 excess electrons. Now, very importantly, the way constrained DFT is implemented in Q-Chem, the constraint regions have to be in a particular order in the molecule block. So right now, going back to this slide really quickly, I have cobalt and then a bunch of stuff attached to it. And I want to make the constraint region as large as possible in order to allow any of the excess charges or spins to relax as they would chemically. So what I have is I have the cobalt, and I have all of the atoms on the cobalt half of this molecule in one constraint region, and chromium and all of that on the chromium region of this molecule in the other constraint region. And in my Q-Chem deck, they're in this particular cobalt, and then following it immediately in the molecule block in the input deck, all of the atoms on the left-hand side of this molecule, and then chromium, and then following chromium, all of the atoms on the right-hand side of this molecule. And they have to be grouped together in these particular orders in order for the way the constraints are implemented to work. Now, I have, I have 4 atoms which are kind of dead in the middle of this molecule, so I don't really want to put them in either the left region or the right region. And that's these 2 mu oxos, the ones that bridge the metals, and the hydrogens attached to them. So this is fine. I can make it so that the constraints don't apply to these. So I have those 4 atoms right here at the end of my molecule section after all of the stuff I'm constraining. Okay. So if we go down to the rem section, so you specify a basis set and a functional like normal. These are just some convergence options. And then in order to invoke CDFT, you use the CDFT-true keyword. And then there are a bunch of options with which you can use to help with CDFT convergence and some of the CDFT output. So really quickly, the CDFT post-DIAS option imposes the constraint after DIAS. The CDFT pre-DIAS option imposes the constraint before DIAS. You can do it either after SCF, before SCF, or both. Default is just after SCF. So the CDFT thrush keyword tells you it works the same way as all of the rest of the thrush keywords in Q-Chem. So it says once I reach a difference of 10 to the minus 5, we'll call CDFT converged. If you CDFT Becky pop to true, you'll print out the Becky populations that were used to impose the constraints. Because as Troy said, all of the Becky populations on the fragments have to sum up to the values of the constraints. Okay, so once you say CDFT true, it tells Q-Chem to look for a CDFT block in your input deck. And this block is where you define your constraint regions. So in the manual, there's 2 ways to define the constraint regions. I'm only going to talk about one of them today, which is the one that I find more intuitive personally, which is to directly constrain charges on one side versus the other side. So in this particular example, I'm only constraining spins. So I do that by specifying S right here for a spin constraint. If I wanted to constrain charges, I would change this to a C, a charge constraint. And the way that this Q-Chem reads this is it puts a net spin or a net number of excess spins of 0 on atoms 1 through 25 in the input deck. So that would be the first 25 atoms in the input deck right here. And then a number 2 excess spins on atoms 26 through 49 in the input deck, which is the chromium half of this molecule. This extra 1 in front here today will always be a 1. This refers to the coefficient of the Lagrange multiplier. So you can also constrain charge or spin differences by screwing around with this number. We're only going to constrain absolute numbers of charges and spins today. So if you run this calculation with Q-Chem, see the output looks something like this, where say normal Q-Chem output, except at some point the constraint is enforced either before or after DIS, and this tells me that one of my constraints was that one side of the molecule has a spin of 0, the other side of the molecule has a net spin of 2. I told it to print Becky populations, so it did. And here are my Becky populations. So if I added up the net spins on my entire first fragment, the net spins would all sum to 0. If I added up all of the net spins on my second fragment right here, those would all sum up to 2. And as you can see, there is some leakage from the metal center over to the rest of the molecule, which is why we included that in the constraint region. And then the rest of it is just as in a normal job. However, the energy of the states, which will appear right here, is the energy of this spin-constrained state, which will be different than the ground state energy if we relax these constraints. Okay, so that was the first example using just constrained DFT. So the second example I want to talk about today is to use constrained DFT configuration interaction, or CDFT-CI, to compute couplings between charge transfer states. Now, the system I'm going to talk about here is the cyclohexane cation dimer, which is a fairly contrived charge transfer system, but it's illustrative and it works pretty well for this. So this particular system is, if you can imagine, you have a cyclohexane molecule with an excess positive charge on it, and there's a dimer, so there are 2 cyclohexane molecules. What is the coupling between the state where the positive charge lives on the first cyclohexane molecule versus the state where the positive charge, the whole, lives on the second cyclohexane molecule? Okay. So in order to do CDFT-CI, I have to define my 2 states. So the first state is going to be the first one of these that I showed you, where the positive charge lives on the top molecule. So this thing right here has an excess charge of +1 and also a single excess spin. Okay, so the other region is normal cyclohexane. It's a neutral singlet, so it will have no excess charge and no excess spins. Again, the charges on both of the states sum up to the total charge that we specify in our Q-Chem input, and the total number of excess spins have to sum up to the number of excess spins implied by the spin multiplicity that we give to Q-Chem. And in this example, I'm only going to be constraining one region because Q-Chem is smart enough that if you only constrain one region, it will use the constraint value for the one region you specify in the CDFT block and the total charge and total spin multiplicity that you specify in the molecule block to figure out what the constraints need to be in order to satisfy this for the second region. So this is one of the states that we specify. The other state is the mirror of this, where the positive charge is on the other cyclohexane molecule. So the constraint region will be for this molecule. The excess charge and the excess spin will be there, and the other one will be neutral. So if we go over to how this looks in Q-Chem, let's see, so here we are. We have cyclohexane. So again, the total charge is +1, and the total spin multiplicity is 2, which means there's 1 excess electron right here. And again, we ordered this. It's not as obvious as it was for the metal centers, but they are in the correct order this time again in the molecule deck, where the first cyclohexane molecule is the first like 18 atoms or so. And then the second cyclohexane molecule is the second 18 atoms or so. All right, so again, in the input deck, you specify a basis set, a functional. Here I used a modified version of PBE0. For all intents and purposes, it's PBE0. And some convergence options. And the stuff that you have to specify in order to get CDFT-CI to work, you specify CDFT-CI true. So you don't actually specify CDFT true here. You only specify CDFT-CI true. And then there are a bunch of options for how to deal with CDFT-CI. So by default, CDFT-CI does not print couplings. It only prints out in the output energies of adiabatic states. So this is what you get when you take your diabatic Hamiltonian that involves the coupling and diagonalize it. So in order to get CDFT-CI to print out couplings, you have to set CDFT-CI underscore print to 1. So there are a couple of other options. The CDFT-CI lambda mode is if you want to specify your own CDFT constraint regions, you can set this to true. This is not really useful in 99% of cases, so the default, which is false, is usually pretty good. CDFT-CI skip pro molecules. So if for whatever reason you want to skip the computation of the pro molecules, as Troy had described, you can set this to equal to true. Sometimes this is helpful for getting a calculation to converge, because since we're doing a constraint optimization, convergence can sometimes be an issue with these sorts of calculations. But usually you want to do these calculations with pro molecules, so the default, which is false, which is not skipping the pro molecules, is good. CDFT-CI does an SVD. This is the threshold for discarding eigenvalues. This says if I have an eigenvalue that's less than 10 to the minus 4, throw it out. These last two, CDFT-CI stop and CDFT-CI restart, are useful because, again, we specified two different electronic states here. We specified the state where the hole is on one cyclohexane and the state where the hole is on the other cyclohexane. Now, often you can get these to converge using the same set of convergence parameters for SCF, for example, SCF convergence thresholds or SCF algorithms or something like that. But if for whatever reason you can't get these to converge using the same set of convergence parameters, you can actually stop the calculation after running some number of states and then restart it again using a second input block that you attach to the end of this one, and use a different set of convergence parameters. And the manual describes how to use these keywords in more detail. And so again, for a CDFT-CI calculation, we need a CDFT block. With CDFT-CI, there's one difference in that we're actually computing two different constrained states. So the two constrained states are separated with 3 hyphens. And then the constraint blocks on either side of those 3 hyphens are specified as they were for the vanilla CDFT calculation. So importantly, CDFT constrains electrons, not charges. So this particular input right here on the top says that I'm going to be constraining -1 electron or 1 positive charge to atoms 1 through 18. And I could put a C here to specify charge, or if I don't put anything there, it automatically means charge. And then I also need to constrain 1 excess spin to atoms 1 through 18. And that S means that I am constraining a spin. So this forms my first state. And my second state is the same as the first one, except I'm constraining the 1 positive charge, or the -1 electron, to atoms 19 through 36, and then the 1 excess spin to atoms 19 through 36 as well. So when I run this job, the output looks similar to before, where we go through multiple different SCF cycles to converge all the different states involved. The very interesting output is at the very end of the output file here, where we can print out the CDFT-CI matrices. So the CDFT-CI Hamiltonian in orthogonalized basis, CDFT-CI performs a symmetric orthogonalization, will give you the energies of the two diabatic states on the diagonal. So this is the energy of diabat number 1 and diabat number 2. And then the coupling in the off-diagonal. So the coupling between these two cyclohexane states, CDFT-CI estimates, is about 0.1 millihartry, or 0.2 millihartry. Okay, so that's all well and good. So I want to talk briefly about a problem that we had noticed with CDFT-CI for computing couplings recently, and that sometimes CDFT-CI does a really bad job at computing couplings. So to show you this, I'm going to show you a second example, which is 2 iron atoms separated by 3.5 angstroms. And if we take the charge transfer to go from iron 2 on the left to iron 3 on the right, and to make iron 3 on the left and iron 2 on the right, and compute the coupling between those two states. So in this case, we have, again, iron 2 on the left. That's -2 electrons, or 2 positive charges, and iron 3 on the right, and then iron 3 on the left and iron 2 on the right. So if we do this using a functional, using PB0, or close to PB0, which is with 20% Hartree-Fock exchange, we get a we get a coupling that is really, really small between these two states. So it's 0.0000006 Hartree. If we repeat this exact same calculation using 50% Hartree-Fock exchange, we get a significantly larger coupling. So this is 3 or 4 orders of magnitude larger, so 0.001 Hartree. So obviously this is wrong. This can't be right. That we have couplings that are many orders of magnitude different in each other just by changing the amount of Hartree-Fock exchange in the functional. We've also noticed non-exponential decay. So if we take this system and try and do this exponential decay plots like Troy showed, they will not decay exponentially. You'll even see an increase in the coupling with distance, which is nonsensical for some of these. And we have come up with a way to diagnose this problem, sort of. So we think that the culprit behind this is partial charge transfer. So normally you would want to have your system defined where one of your states has an electron or a hole on one fragment, and your other state has an electron or a hole on another fragment. And in that case, you can form diabatic wave functions, which have a nice overlap. And as you take those apart to infinity, that overlap will decay exponentially because wave function tails decay exponentially, and thus your coupling will decay exponentially. However, if you have systems with a lot of degeneracy or near degeneracy, you can imagine transferring fractions of electrons, so parts of electrons from one state to these nearly degenerate states. In which case, one of your diabatic wave functions isn't local. It spans both fragments, and as you pull these molecules apart, the wave function doesn't decay exponentially because there's some constant overlap there. And thus your coupling won't decay exponentially and you won't get exponential decay. And the hypersensitivity to Hartree-Fock exchange is also explained by this. So one way to tell if this is going on in your system or not is to look at the eigenvalues of the difference density matrix. So this is if you take the density matrix on the donor fragment and the density matrix for the acceptor fragment, you can look at the eigenvalues of this difference density matrix. And if there is whole charge transfer, so if entire charges are being transferred, all of the eigenvalues will be either 0 or 1. And if there's partial charge transfer, some of the eigenvalues will have a magnitude less than 1. So as a simple way, you can just look at this sort of metric where you take sums of lambda squared minus lambda to the fourth in order to tell you if this thing is small, then we have whole charge transfer, and if this thing is large, then we have partial charge transfer. We talk about this problem in this communication that came out recently if anybody's interested in learning more about it. Okay. So the third example that I want to move on to is computing barrier heights with CDFT-CI, so the very last thing that Troy talked about. And the system that I'm going to be looking at for this is if you take H2 and OH and react them to get hydrogen atom and H2O. Okay. So the system looks something like this. So in order to do a barrier height calculation, your two CDFT-CI states have to be, one of your states has to represent the reactants and the other state has to represent the products, and then we're going to do a transition state search using Q-Chem. So the first state, we're going to divide it so that our reactants are H2 and OH. So H2 is a neutral singlet, OH is neutral, but it's a radical, so there's one excess spin. And we'll just constrain that and let Q-Chem take care of the H2 constraint automatically. Let's see, our other state is going to be a hydrogen atom with one excess spin and no charge, and then a water molecule, so H2O, which is a neutral singlet. And we'll just constrain the water molecule and let Q-Chem take care of the hydrogen atom. Okay, so let's see if we do that here. Okay, so I have here in the input deck again OH and then H2 in that order. The overall system is a doublet, so it has one excess spin. And there are a lot of rem variables this time just because finding a transition state is very hard. So convergence is very, very tricky for these, even with CDFT-CI, maybe even more so with CDFT-CI because you have to worry about the constraint convergence, which is always a problem. So we're doing a transition state search with CDFT-CI. We have a ton of convergence stuff right here. some more convergence stuff with the CDFT part of CDFT-CI. And then one REM variable that I want to mention, I don't think this one's documented in the Q-Chem manual, but the CDFT-CI prom guess variable here determines what method to use for the initial guess for the promolecule densities. So by default, you can, for initial density guesses, you can do things like diagonalizing the core Hamiltonian, or using superposition of atomic densities, or reading something in from a file, like normal in Q-Chem. By default, the CDFT-CI prom guess is set to 0, which does a superposition of atomic densities, or a SAD guess, for every geometry step. In a transition state search, you'll do SCF, you'll compute a gradient, you'll take a step, you'll do SCF again, you'll compute a gradient, you'll take a step again. This will reset the density guess using superposition of atomic densities every time you do a step, which could be harmful for convergence, for finding this transition state. Setting this to 1, we'll do SAD for the first guess, and then read in the previous step's density for all subsequent steps, which could be more helpful for convergence. So that's what we've done here. Okay, so again, the CDFT block of this. So we want to constrain, again, going back to our states from before. One of our states is going to be H2 and OH. Our other state is going to be H and H2O. Okay, so right here we have atoms 1 and 2, which, going back up to our molecule block, are the OH fragment, are going to be constrained to have 0 excess charges and 1 excess spin. And that's going to be state 1. State 2 is going to be the first 3 atoms, which is the water molecule, atoms 1, 2, and 3. We're going to have 0 excess charges and 0 excess spins. So this just defines what the 2 molecules in our reactants and products are. And then if we look at the output for this, let's see. Eventually, our optimization will hopefully converge, and the final transition state energy is minus 76.9 Hartree. Okay. So if we want to do a barrier height calculation, we can take the transition state energy that we got from CDFT-CI and subtract off the non-constrained ground state energy of the isolated H2 and the non-constrained ground state energy of isolated OH. And this will give us the barrier of this reaction coming from the H2 plus OH side. We can also do this coming from the other side, which might give different barriers, might give the same barrier. This is one of the reactions that we talked about in this reference, analytic energy gradients for CDFT-CI. We did a whole bunch of reactions and found that the accuracy, again, was pretty good for these barrier heights. Just to give you an idea of how good, so if you look at, by this procedure, the CDFT-CI reaction barrier is 6.4 kcal per mole. If I were to do this reaction barrier with just B3 lip, it would be 0.8 kcal per mole. And the reference calculation for this is about 5.1 kcal per mole. CDFT-CI is within 1.5 kcal per mole accuracy. B3 lip is within about 5 kcal per mole, 4.5 kcal per mole accuracy. And we notice about an 8-fold improvement in this case. Okay, so with that is all I have today for this. So I think we can pass it back over to Zhengting and go to questions.
Thank you, Troy and Mike, for the excellent presentation. Now let's start the Q&A session. And so everyone here in the audience, please type your questions in the question box of your control panel. And currently we only have one question. I think that's for Mike. So can you share, that's from Xiaohui Chu. And Mike, can you share the example input and output files? Mike?
Yes. So the example, I can give them to you. Like to make them available in some manner.
Yeah. So if someone is interested into getting Mike's or Mike's examples, you can write either to Zhengting or me, and we'll make sure that you get those files. And so again, let me see the question coming. Okay. Let me read another question from Xiaohui. So he is asking about the procedure. In a charge transfer calculation, for example, in the cyclohexane dimer calculation, what kind of method and state should be used for the geometry optimization?
Yeah, so
Yeah,
this
so this
is
pretty
tricky,
tricky, I guess.
depends on
Depends
what
on
you
what you want for,
I guess what you
I
want to
guess
call
what
your
you want to
ground
call your
state.
ground state.
For
For
these
these particular
calculation,
calculation,
I just
I just
a
a
B3 lip
B3 lip
unconstrained
unconstrained
optimization
optimization
and
and
call that
call that
my ground
my
state.
ground
And then
state. And then I form, well,
Muted.
I did the B3 lip, or sorry, the cyclohexane cation dimer B3 lip unconstrained optimization. So I allow the charge to delocalize over both if necessary, and then to form the coupling, I constrained it on one versus the other. So I hope that answered your question.
Unmuted.
Okay, next question is about the running DFT calculation in parallel. Will there be parallel capability for constrained DFT in the future?
Muted.
So we haven't started implementing the so it was, I think, at one point in the past in parallel before when Q-Chem was using the OpenMP, right, Mike?
yes.
Yeah, and then it switched to the MPI and it stopped working in parallel. It's not trivial to get it back being parallel, although it's not. It's not trivial, so we haven't put a lot of effort into it yet. Although we get frustrated because we run jobs and they all have to be serial jobs. So yeah.
Unmuted.
And Tim, do you have anything to add there about the parallel capability of constrained DFT? Have you looked into that?
Yes, we will implement as soon as possible. Back to Ihan.
Okay, the next question comes from Dimitri Claudio, and his question is, it's not clear for me what exactly from CI enters into the CDFT-CI calculations. Maybe Troy, probably we need to go back to your slides.
Yeah. Let me hold on. I gotta
reopen my slide.
Unmuted.
So the general.
Just 1 second. We need to make you the presenter, Troy. Why don't you do it yourself? I mean,
Okay.
Make yourself the presenter.
So the general. So yeah. So it depends. I can understand the confusion there. The use of CI, but we're not doing a CI calculation like MCSCF or CISD or something like that. So the idea is that whenever I build the Hamiltonian as a matrix like this, this is the same thing that one does in configuration interactions. So each of these states, the reactant state and the product state, is a configuration. It's a many electron state. And so when I compute matrix elements between reactant and reactant and reactant and product and product and product, I'm inherently computing the interaction between these configurations, and then the key step in any CI procedure is finding an eigenvalue of the matrix. And so I have a matrix here, and I find its eigenvalue, or at least its generalized eigenvalues. And so in that sense, that's why we call it CDFT-CI, because it's got this configuration interaction feeling to it at the end. But we're not using a CI calculation to say build the DFT or anything like that. So.
Okay, let's look at the next question from Joanne Quinn. And his question, I think, is about the size of the molecules for constraint DFT calculations. Is there a practical restriction in the size of the molecules? Put in another way, what's the largest molecules you have looked at so far?
Yeah, I can take this one.
So,
With
Muted.
DFT not being implemented in parallel in Q-Chem right now, I think it's really how big are you willing to wait for, or how big of a molecule are you willing to go in order to do DFT on a single core. So constrained DFT by itself, it has about the same cost as DFT. And if you do CDFT gradients for an optimization, that has about the same cost as a normal DFT geometry optimization. So I would say on a single core, you could probably get up to 100 atoms, 150 atoms, something like that, maybe even larger, 200, 300, if you want to wait around a couple of weeks. I think we've done several thousand bases, like 3,000 or 4,000 basis functions. Yeah, routinely. So, yeah, something like that. So CDFT-CI is a little bit of a different story because you have to do for a 2x2 Hamiltonian 4 SEF calculations for the 4 different states involved. That's about 4 times the cost of a normal DFT calculation. And if you want to do,
and more importantly, 4 times the convergence headaches.
Yes. So you can, I guess, do a bit smaller there, but not terribly much smaller. If you want to do any kind of optimization, so ground state or transition state searching using CDFT-CI, gradients right now are pretty slow. We're working on making them faster, but it's, I would say, you're probably limited to, I don't know, maybe 150 atoms or so around there with a reasonable basis set.
Unmuted.
Okay, the next question is about the comparison between constraint DFT and CASPD2. And the question is, have you done any comparison between constraint DFT and CASPD2 calculations?
No.
Unmuted.
No, we haven't done any of those comparisons. They would be interesting comparisons to do, but we like Q-Chem and we use it, and Q-Chem doesn't have CASPD2, so then we can't compare. No, but we could get Turbomol, or actually I don't know if Turbomol doesn't have it either. I guess MolPro has. Anyway, yeah, we don't have easy access to a CASPD2 code that we like, so then we haven't done the comparison.
And I think we have one final question here, which is about the calculation for transition states. And let me just read the question. I didn't understand exactly the calculations of the electron structure for the transition state. You basically perform 2 calculations at the transition state geometry, right? Is the constraint DFT transition state electron structure some sort of weight between the 2 calculations based on combination between a reactant and a product states? And for that, we might want to go back to our slide on transition state.
Yep.
Yeah, so I'm happy to get into that one. So to answer the question, you're right on track there. So
Muted.
the transition state, you do 2 calculations, a reactant-like calculation and a product-like calculation. And the wave function that we're using in constrained DFT at the end of the calculation, once we do the CI, is a superposition of reactant plus product. So we determine by diagonalizing this matrix the right coefficients, C1 or C2. I see I'm inconsistent in my notation. These should be CR and CP. But in any case, these coefficients are determined by solving this eigenvalue eigenvector problem. And that tells you how much the wave function looks like reactant and how much it looks like product right here at the transition state. Because sometimes you have an early transition state where it looks more like reactant. Sometimes you have a late transition state where it looks more like product. And the CI figures out the correct weights there.
Unmuted.
Okay, great. I think that's almost all the questions we have for now. And if you have any more questions, you can find Troy's email from his website at MIT. And you can email Troy directly, or you can email us. And with that, I want to thank Troy and Mike again for this great presentation. And I want to thank everyone for attending.
This concludes our webinar. We would like to thank Troy Van Voorhees and Michael Mavros for their excellent presentation, as well as Yihan Shao and Jinjing Dan for their work at organizing, moderating, and running the webinar. Should you have any questions, please feel free to contact us by emailing either Jinting or Yihan at the email addresses noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.